Greetings to all and welcome to this lecture. We are in module 7, lecture number 2. This is the last lecture where we are going to discuss about strong inversion separately. In this lecture, we will see what is the role of alpha in the derived equation IDS is equals to W divided by L mu into COX dash into VGS minus VT into VDS minus alpha by 2 VDS square. Alpha plays an important role in designing and optimizing your model. We will also see how we can relate the potential with position. So, these are the learning outcomes of this lecture, which helps you to understand the role of alpha in the model, which we generally ignore when we are going for hands-on calculation or simple calculation. We consider alpha is equals to 1. This will also help you how we can relate the potential with respect to position along the channel. Let us do a quick recap. In previous lecture, we said that we can simplify our model of drain current by considering body reference and source reference We have said that both models will give you a different insight. Body reference model will give you an insight that my drain current is linearly varying with drain to source voltage, and hence we can capture this region of operation precisely, which says that my drain current is linearly rising, meaning MOSFET acts as a resistor, as a voltage controlled resistor. However, the body reference model cannot guarantee or cannot give you a picture of the symmetricity of the device, meaning which terminal you can take as a source and drain, it is not well defined. Whereas the source reference model is another approach to find out a simple current equation, which we use in our hands-on calculation, that IDS is equals to VGS minus VT into VDS minus alpha into VDS square divided by 2 with some constant as mu into COX dash into W divided by L, where we have seen that how this alpha is coming into picture, which is nothing but alpha is equals to 1 plus gamma divided by 2 root psi SE, where psi SE is an expansion point. For body reference model, expansion point is nothing but psi SL plus psi S0 divided by 2, whereas for source reference, expansion point is nothing but psi S0. It means the potential near the source. We have also derived a closed form equation which says that what is the range below which my current will be in linear region and what is the range of voltage above which my current will be in saturation, which we defined as VDS dash as VGS minus VT divided by alpha. We derived this equation by simply assuming that this equation will be obtained by keeping VDSN slope with respect to VDS is equals to 0. Let us move further to define our equation in a more simpler way. So, I am defining a new parameter which is eta. Eta is equals to 1 minus VDS divided by VDS dash, which is nothing but 1 minus VDS divided by VGS minus VT by alpha, right? Or you can simply write VDS divided by VGS minus VT is equals to 1 minus eta by alpha. We will use this parameter later in our models to simplify the analysis. So, if I define eta, eta is equals to 1 when VDS is equals to 0, right? At VDS equals to VDS dash, eta is equals to 0. Let us see and check whether this eta equation is simplifying our model or not, meaning I can simply replace IDS is equals to IDS dash into 1 minus eta square, where IDS dash is a saturation current equation, which is nothing but given by this W by L mu into COX dash, VGS minus VT whole square divided by 2 alpha. So I can just check whether by solving this equation I am getting IDSN or not, where IDSN is what? The current in non-saturation region. 1 minus eta. What is eta? It can be written as 1 minus VDS divided by VDS dash whole square. You can simply use A minus B whole square. So IDS dash into 1 minus 1 minus VDS by VDS dash whole square, minus and minus plus 2 times of VDS divided by VDS dash. So this will get cancelled. You will left with IDS dash, take VDS common, or better you take VDS dash square common. You will left with 2 times of VDS into VDS dash minus VDS square, right. Now what is IDS dash is this equation. So I can simply use IDS dash is equals to W by L into mu into COX dash into VGS minus VT whole square divided by 2 into alpha divided by, if I do VDS dash square, meaning you need to multiply with VGS minus VT whole square into V into alpha square, right, because VDS dash is nothing but what? VGS minus VT by alpha. If you do so, this term will get cancelled, alpha get cancelled, you will left with alpha by 2. So you insert the alpha by 2 in this bracket, ultimately you will ended up with IDS is equals to W by L mu into COX dash, alpha by 2 you take inside to this bracket, you will left with VDS into VDS dash into alpha minus VDS square divided by 2 into alpha. Now what is VDS dash? Again it is VGS minus VT divided by alpha into VDS. So alpha and alpha get cancelled. Ultimately you will ended up with IDS is nothing but IDSN, which is given by W by L into mu into COX dash VGS minus VT into VDS minus VDS square into alpha by 2, right. This is the current equation in non-saturation. So I can simply define a single equation for IDS by this. We will use this equation eta in our subsequent analysis. Now let us analyze what is the role of alpha. As I have already mentioned, the alpha plays a very significant role in the optimization or the modeling what you are doing for current, correct. So in current you are getting alpha as W by L mu into COX dash into VGS minus VT VDS minus alpha into VDS square divided by 2. In a very simple approach we considered alpha is equals to 1. Now what alpha is? You go back your analysis and check, we have derived a equation between minus QB dash by COX and psi s, meaning we plotted a graph for linearizing this QB dash to avoid the square root term, right, and we said that alpha is nothing but 1 plus gamma divided by 2 times of root psi SE. Based on this expansion point we drew 3 lines, right. If alpha is equals to 1, meaning this slope is 0, so this point can be represented by this line C. If psi SE is equals to psi S0, meaning what? The source reference model, then we are actually taking this point which is A, right, and we said that in that moment that there is another approach which should be very close to capture this solid line, that is what the line B, right. So ultimately alpha is nothing but the slope of these lines, which shows that how precisely I am capturing the bulk charge. Now let us consider the first case when alpha is equals to 1, meaning we are talking about which line? Line C. If you do so, it simply says that your bulk charge is this solid line, right. So let me change the color to green. This is your bulk, charge, accurate bulk charge. But what you are doing by this point C or the line C, you are actually capturing bulk charge as underestimated, right? You are underestimated or you are underestimating the bulk charge. If you are underestimating the bulk charge, what about the inversion charge? It will be overestimating, because minus COX dash VGB minus V flat band voltage minus psi S minus QB dash. If it is this is underestimated, this will be overestimated. If QI will be overestimated, meaning what? The current will be overestimated. Meaning, if you consider alpha is equals to 1, the precise model, for example, this is your experimental data, and when you plot with alpha is equals to 1, it will overestimate, right? It will not capture precisely. That is what you need to choose alpha wisely. Now, what will happen if I considered alpha is equals to 1 plus gamma divided by 2 times of root psi 0, right? Meaning we will consider the line A. If you consider the line A, then you see the bulk charge is overestimated now. At that moment, what happens is the inversion charge will be underestimated, and hence the current will be underestimated. So you will get something like this, correct? Meaning you have to choose the alpha precisely between 1 to alpha dash or alpha 1, right? Where alpha 1 is the value of alpha which is defined for source reference model, which is 1 plus gamma divided by 2 times of root of psi 0. We can see here that when we are plotting, for example, this dotted this lines with the dots is pure experimental data, or the data obtained by complete all region model, which is a correct observation. Now, when you go for alpha is equals to 1, ultimately this is the graph. When you go for alpha is greater than 1 or alpha 1, you will get this graph. However, you need to tune alpha between 1 to alpha 1 to get the precise results. That is what alpha plays an important role, which we generally ignore when we go for a simple hands calculation in analog circuit or digital circuits, right? A simple approach we can opt as using some fitting parameters. So alpha can be defined as 1 plus d2 into gamma divided by 2 times of square root of psi naught plus VSB plus phi 3. In general, we consider d2 as 1 and phi 3 is 1, right? So to match the data, again this is an experimental fitting parameters. Again, this is a fitting parameters which helps us to fit the model against the experimental data or the data which we extracted from characterization, right? Now, we can simply say that the accuracy of the model is completely depends upon the alpha, where alpha is again dependent upon gamma. So we can simply say the alpha is a function of gamma, and hence the gamma will decide the accuracy of the model. If we choose alpha is equals to 1, then this model is highly inaccurate when the value of gamma is very large. So ultimately the gamma or the body effect decides what is the tuning parameter, right? You have to use, or the fitting parameter you have to use to match your model or to derive your model to match the experimental data. Let's go and see, can we relate the potential with respect to position along the channel. So let us consider I do have a MOSFET and this direction is X direction. So this is N plus, this is drain terminal which is VDB, this is source terminal VSB, and this direction is X side, this direction is Y side, right? So what we are going to represent, can I represent the potential variation along X with respect to position, right? This position which is X. So if my channel exists between 0 to L, I can simply say my channels, my carriers are moving like this and they are reaching to drain. But if I take any position at x, right, then I can simply say the voltage at this point is VCB of x, right. This VCB is again with respect to body as a reference. At this position, this can act as a virtual drain. So if I consider this is the channel length, right, in general, and then I will integrate this dx between 0 to L, I can relate this position with respect to voltage. So let's get started to analyze that complete equation IDSN, right, which was nothing but W by L into mu into COX dash VGS minus VT into VDS minus VDS square divided by 2 into alpha, right. So in general, I can represent IDSN as some function of VGB, VSB and VDB. Here we are considering with respect to body as a reference. Similarly, at some point x, this voltage is represented by what? VCBx. So this function will be same, W will be same, but the position we are just calculating till x. So this will be x, h of VGB, VSB, but this function will be what? VCBx, a general function of x. That is what we need to relate, how this function is relatable with the terminal voltages VDB or VSB. One thing is important to note here, that VDB is equals to VDS plus VSB, right, which we have already derived as VDS is equals to VDB minus VSB. So if the voltage is represented in terms of body as a reference, then you should add VSB in the voltage which is represented in terms of source, that you should take care of. So if I need to derive this term, VCBx should be equals to some function of x. This x function is what? Related to source, right, source as a reference here, plus VCB. So let's derive this equation as both sides the current is same, because the current is same flowing into the MOSFET. We are just relating the x with respect to VCB. So I can get x divided by L is equals to that function, which is a function of VGB, VSB and VCB, right, and L is equals to this. Here it will be VDB and this function will be VCB, because this is in inversely proportional, right. So if you divide those, x by L is equals to what? VGB function in VSB function and VDB function divided by h of VGB, VSB and VCB of x, correct. So this is VCB of x and this is VDB of x, VDB. Okay, so let's see how we can relate the potential along the position in the x direction. So this is our MOSFET, this is N plus, this is drain, this is source, this dimension, this direction is x and this is y. So we wish to relate the potential along the x with respect to x. We have already plotted this graph earlier. We said that when we change the x direction, then this psi SL or psi S0 varies like this, correct, or the surface potential, if we keep psi S0, the surface potential at the source, it varies linearly, monotonically towards the channel L, this is x direction, and this is psi SL greater than psi S0. The same thing is coming up when we are talking about strong inversion. Then psi S0 is nothing but phi naught plus VSB and psi SL is equals to phi naught plus VDB. So the potential along the channel will monotonically increases towards the drain. So when you are going from source to drain, the voltage will monotonically increases. So can we relate this increase in potential along this distance? Considering the current which flows in the MOSFET from drain to source is constant, meaning if this is the drain end, this is the source end, there will be a current IDS. Let us consider I define a point X here, and here also if you are in strong inversion, this can act as a virtual drain, and hence the current will be same. So I can simply write in the non-saturation current can be given as W divided by L into some function of VGB, VSB and VDB when you are considering complete length of 0 to L. So this is your drain. So the first equation, equation number 1 is for this is source, this is drainage. Now second equation I can simply relate if the source is fixed but the drain is now virtual. So this is X. So I can simply rewrite without changing anything that current will be same. So IDSN W divided by X instead of L, now this distance is what? 0 to X, right? So it is X. Same function I need to use H, which is function of VGB, VSB, but now the VDB value is the maximum value of VCB. Ultimately we are actually changing VCB along the X, which we said that VCB at 0 is equals to VSB and VCB at L is equals to what? VDB. So these are the extreme values at the source and drain end. However, if I want to calculate for a particular X, then I need to take it as a function of X. The another thing to note here is the function H, what we derived in our previous analysis, is based on source as a reference. In the sense, this function is nothing but W divided by L mu into COX dash into VGS minus VT into VDS minus VDS square divided by 2 into alpha. So if I want to represent these terms in terms of source as a reference, then I need to take utmost care that VDB is nothing but VDS plus of VSB. So if we derive this equation for VCBX, then VCBX is equals to what? Some function which is reference to source plus VCB, correct? This we have already discussed that VDS is nothing but what? VDB minus VSB. So I just put VSB here and I am representing this equation, this voltage equation with respect to body as a reference. So let us do some calculation to find out the relation between X and VCBX. So what we have found here is X by L is equals to some function which is VGB into VSB into VCBX divided by some function VGB, VSB and VDB. Here I am using the function which what we have derived is with respect to source. So I will take what? Mu into COX dash into VGS minus VT into, instead of Vx will take VDS, instead of VDS will take Vx minus alpha Vx square by 2 divided by mu into COX VGS minus VT into VDS minus VDS square into alpha by 2. This is the function what we have derived. The function means the current, right, and the current is constant. That is what we are writing in this way. From here this mu into COX will get cancelled. Ultimately you will get with what? Alpha into Vx square divided by 2 here minus VGS minus VT into Vx plus VGS minus VT into VDS minus alpha VDS square divided by 2 into X by L is equals to 0. Let's solve this equation, but before that, as it is independent of x, I am considering this as a. So my equation will be alpha into Vx square by 2 minus Vgs minus Vt into Vx plus a is equals to 0. You can simply solve as Vx is equals to minus of b means Vgs minus Vt plus minus square root of Vgs minus Vt whole square, right, minus 4 times a into alpha by 2 divided by 2 times a or alpha by 2. This 2 do get cancelled. You will left with Vgs minus Vt divided by alpha, right. Now you need to choose which sign you will opt for, positive or negative. First take alpha inside, so it is Vgs minus Vt by alpha whole square minus 4a alpha alpha, so it will become what? This is 2a into by alpha, because you are taking alpha square inside, right. Now shall I choose positive sign or negative sign? I need to choose negative sign, because at drain edge, when this Vx become Vdb or Vds, then what will happen? The maximum value will be what? Vgs minus Vt by alpha. That is the saturation value, and hence if you are taking the value of Vcb before drain, then definitely it will be lesser than Vgs minus Vt by alpha. So I need to choose negative sign, which you are calculating Vx is equals to Vgs minus Vt by alpha, negative, take Vgs minus Vt common or square by alpha common, you left with what? 1 minus, this is 2 into a into alpha by Vgs minus Vt whole square. Here this equation can be written as Vgs minus Vt by alpha 1 minus square root of 1 minus 2a alpha by Vgs minus Vt whole square. Let us call this equation as equation number 1. We will come back to this equation and put the value of 2a alpha by Vgs minus Vt whole square. Okay, 2 alpha divided by Vgs minus Vt whole square into a. A is defined here. It is what? X by L into Vgs minus Vt into Vds minus alpha into Vds square divided by 2. So x by L you keep it outside and rest you go in the means put these parameters inside the bracket. Vgs minus Vt divided by Vgs minus Vt whole square into 2 alpha into Vds minus alpha square 2 into Vds square divided by 2 into Vgs minus Vt whole square. You see 2 and 2 get cancelled. Here this Vgs minus Vg and this get cancelled. Now you are left with a factor which is defined as 2 alpha Vds divided by Vgs minus Vt minus alpha Vds divided by Vgs minus Vt whole square. We have already defined a parameter, that is what? Eta. Eta is equals to what? 1 minus Vds divided by Vds dash and 1 minus Vds. Vds dash is what? Vgs minus Vt into alpha. You can see alpha Vds divided by Vgs minus Vt can be written as 1 minus eta, right. So this equation here, this equation is can be written as x by L into 2 times of 1 minus eta minus 1 minus eta whole square. So you solve further, x by L into 2 minus 2 eta minus minus 1 minus eta square, this will be 1 minus eta square, yes, then minus and minus plus 2 eta, correct. So you will left with, this will be plus like this. So ultimately x by L, 2 minus 1 is 1, this will get cancelled, minus eta square. And now you put back into equation number 1, ultimately you will get this, correct. We are getting that same equation as Vgs minus Vt by alpha, Vgs minus Vt by alpha into 1 minus square root of 1 minus x by L into 1 minus eta square. Yes, here we need to add VSB. Why? Because I have already explained that if you are representing VCB with body as a reference, then you have to add VSB plus Vx, because this equation was for Vx, where Vx was measured with respect to source as a reference. So you need to add this, and this will give you how my potential varies in the channel along x, right. So at any point of x, if you want to calculate the VCB, you can simply calculate by this equation. The idea of this equation helps you to understand few more insights, that is, if you see VDS is very small, the rise in VSB is very small. However, when you go near the drain, the rise in VSB is steep. Why it is so? If you observe here, then the change in the voltage is much more to change in the inversion charge, right. So you have to apply less voltage to change the inversion charge near the source, because it is highly inverted. However, when you go towards the drain end, then Qi goes to 0. So you need to change the voltage much high to get change in the inversion charge, and hence this slope, the steepness of the slope is higher at the drain side, correct. So in previous equation, what we have derived so far will give you actually at Vd equals to Vds dash, right, at x is equals to L, when Vds is equals to Vds dash, Qi is actually goes to 0, which is physically impossible, and hence this is the limitation of that model. That is what we need to take care about, how you are incorporating Qi dash, right, and Vd, correct. The another limitation of this model is it is not capturing the diffusion current, right. The another part of this model is that it is not capturing the diffusion current. We have derived only the drift part of the equation, considering our device is in strong inversion. Let me summarize here. In this lecture, we have seen that what is the important role of alpha in modeling of current equation, which we said that IDS is equals to W divided by L mu into COX dash into VGS minus VT into VDS minus VDS square by 2 into alpha. The value of alpha is very important to optimize your model to match the experimental data. The second part, what we have discussed in this lecture, is how you relate the potential which is varying between source and drain, which is nothing but VSB to VDB along the x. So this is VDB, and along at any point of x, how can you derive that? We said that VCBx is nothing but VSB plus VGS minus VT divided by alpha into 1 minus square root of 1 minus x by L into 1 minus eta square. Okay, so we'll stop here for today. Until then, take care.